Hello. So yesterday morning, Brian started, he said, it'd be great if we had some hacking sessions at this RosCon. And I remember thinking, I was like, when will that happen? There's no time. So Albert and I sat down, and actually, mostly Albert, did some hacking. And we got Move It to run on Baxter. If you could play the video. So first of all, thank you very much, Chris. I just went to the booth and said, could Rethink give me a URDF of your robot? They did. About 10 minutes later, we had Move It running in simulation for the Baxter. And then with a little bit more help from Albert, we actually had it running in hardware. That's about it. I probably used 1 minute. Let's give it to the next guy.
Anyway, hi, I'm Yashodhan Nevatia, and I'm going to talk a bit about using ROS for planetary rover operations. So we're currently working on a European project called FASTER, which, as you guess, is trying to improve the traversal speeds of planetary rovers. Right now, as with Curiosity and older rovers, they face a lot of very mission-critical hazards. So all traverses are very carefully planned by large teams of people at mission control. And what we're trying to do is use a scout rover or small lightweight rover to go ahead of the rover, of the big mission rover, to try and detect any of these hazards. So the primary rover can then move faster without taking care that much and also do more autonomy. So as you see up there, the components of the system are the main primary rover, the scout rover, a number of sensors we're going to use to detect hazards, and a cooperative autonomy system. So the scout rover, we are going to keep it very, very simple to make it as small as possible. It's just going to do path following. The primary rover is going to do all the perception planning and then give a path to the scout rover, which is going to follow. And to do this, we're planning on using a combination of ROS with the genome framework that was developed at LAS in France. And you can see what all goes into a space rover, into a planetary rover. We're just going to focus on 3 parts of this big architecture: the task planning or task scheduling, guidance, navigation, and control, which means mapping, localization, and path planning, and then scout localization, so trying to detect the position of the scout rover from cameras on the primary rover using image processing techniques. And of course, we're going to test it out on a planetary rover that's there in the UK at Astrium. But before they allow us to do this, we have to test it in simulation. So we're going to use Gazebo or USAR Sim. We still haven't decided. And to achieve this, we've begun importing actual terrain information from Mars into both simulators, as well as developing the rover models for both the Scout rover and the planetary rover itself. Anyway, thank you, and you can feel free to contact me if you have any questions.
Yeah, it's right here.
Just autonomy lab. Thank you.
So, hello everyone. My name is Mani Monajemi from Autonomy Lab at Simon Fraser University in Canada. I'm the maintainer of AR drone driver for ROS. What I'm going to show you is a video of a demonstration experiment that we did last month in Toronto. In this video, you will see a fully autonomous integrated system of a human multi-UAV interaction, mono-SLAM, and visibility-aware exploration and planning. This experiment is part of the Canadian-wide field robotics network that we started just this year. And ROS is one of our main candidates for doing system integration between 9 different universities. So the video is sped up, so I talk instead of the human in the video. So the human picks a robot, says you, name the robot, you're green, picks another robot, says you, and says you're red, and now asks the green robot to take off. The robot now does mono-slam initialization. When done, the user can engage with robot and ask the robot to explore a certain direction, a specific direction. Now the robot is doing visibility-aware planning while doing slam. Now the user asks the red robot to take off. Again, ask the robot to explore that direction. And now we have two robots doing exploration in the environment and mapping. And now the user asks the red one to come back to the base. And now ask the robots to land. Thank you.
Hi, my name is Yogesh, and I'm a PhD student at McGill. So what if you had robots which, instead of sensing pixels and like low-level sound waveforms, they could sense the world in terms of, oh, there's an object here, I'm in this room, I am outside, I'm inside. And what if you did not have to train them for every one of these things which you want to detect? What if it could automatically learn different ideas and objects which exist in the world, and then you can make your life easier further on. So the general idea behind this pipeline I'm working on is that if certain observations exist together in space and time, there's a good chance they belong to the common underlying cause. So when you always see eyes and nose together, there's a good chance that there's a common thing which we humans call as face that exists, and that's responsible for producing those observations. If we hear birds chirping and like wind on our microphones, there's a good chance the context of those observations is outside. So this perception pipeline deals with automatically doing this. So can you go to the next slide? So the way this works is that we make a bunch of observations, and we have a bunch of these contexts, which we call as topics. Sorry for choosing the name topics. So it's nothing to do with ROS topics. And the goal is to represent what we observe in terms of these topics. So these topics are automatically learned. These topics could be being outside, being different objects. And each topic is represented as models in terms of low-level observations, the distribution of low-level observations. So, can you go? So the benefit of doing this is that, so this has several applications. We can use this with both vision and audio. It could be used for things like loop closing, doing things like summarizing all the data you have, detecting surprises, and autonomously exploring the world. So instead of talking, I'll just show you a bunch of examples of this running. So in this first example, I'm just using audio, and the histogram corresponds to different contexts which the robot is in. So right now, yellow was the lab. So as we go into the stairs, it'll change to the green topic, which automatically learned that it corresponds to the stairs. And can we move further in the video? So here I'm doing it with video, and automatically the robot learns, gives different parts of the room a different color label, which corresponds to a different context. Here I'm using the same framework with my underwater robot, and I'm doing, all what I told it to do was find the context which is the rarest and follow it. And all of a sudden we have a pet like robot which goes around chasing surprising and interesting things. Thank you.
All right, take it that way.
Okay, hi, my name is Christian and I'm from the Computer Vision Group at the Technical University of Munich. And I want to show some recent work we did on dense visual odometry for RTBD cameras. So let's have a look at the first video. Okay, so here we have an RTBD camera, like a Kinect, moving around the scene, which is represented by this little red box, and we actually want to estimate its trajectory just from its images. And so standard approaches to visual odometry extract sparse features and compute the motion from this. But in our approach, we use all image information to get more precise estimates. Okay, back to slides. So it's a frame-to-frame matching method. So we have no history, so we have a constant memory footprint. Nevertheless, it's highly accurate and we only have little drift. And the good thing is also it uses all image information. We can run it on a single CPU core at camera frame rate. And if you like to try it, you can download the source code from our GitHub page. And we already tried it on a quadrocopter and for a handheld Kinect, but it would be interesting to see how it performs on other robots. So if you're unhappy with your current visual odometry, give it a try. Okay, and let's have a look at our extensions to this. So here we integrated it into a full SLAM system and did the drift correction and then 3D reconstruction, and we obtained a nice 3D model of our 40 by 10 meter floor at our department. And at the core of this algorithm there's this dense visual odometry method. Okay, thanks for your interest. And
hi, I'm Mr. Fernandez from Universitat Pompeu Fabra in Spain and from Griffith University in Australia. And I'm presenting next, please, a library called TX-ROSPy, which is an asynchronous library for the RosCon API and protocols. It uses Twisted, which is basically an implementation of the reactor pattern. And both are open source. You can use them and feel free to use them and contribute and whatever. The reason I did the TX-ROSPy library was to see how feasible it was to replace parts of the ROS stack. For example, with TX-ROSPy. No. You go. Yeah, thank you. With TX-ROSPy, you can replace TCP-ROS with another RPC mechanism, for example, Thrift, or replace TCP altogether and use something more interesting like AMQP. TX-ROSPy is fully compatible with the existing libraries like RosCPP, ROSPy, RosRuby, and I'm not sure if there are any other libraries. Yeah, RosC. And here's a simple example, and it looks sequential code, but it's actually asynchronous. It's non-blocking because it's using something called inline callbacks decorator. This is a very simple example, which this one is a bit more interesting. You got a server, and the response to a request doesn't block at all, which is good for servers that need to accept several requests at the same time. And thank you. Please have a look at the GitHub page and contribute, and well, tell me what you think.
Good evening, everybody. I want to introduce you ROS.org. Probably, you know, just kidding. Just one part of this that's highlighted here. It's mentioned that actuator level control also can be done within ROS. But in the later, I want to show that probably it's not a good idea. Next, please. So if you have two ROS, one stands for robot operating system and the other one something based on real-time operating system, then it's better to divide the tasks in this way. Actually, all of the time-consuming tasks within ROS platform, which we need mostly flexibility, modularity, and lots of things to combine with each other. But on the other hand, for dead reckoning, sensor fusion, and any part of control, when we do it in ROS, actually the performance and the smoothness of the final result, it's not satisfying in practice. Especially, for example, in position mode control, you will receive lots of vibration. In velocity mode control, you will receive imprecision movements. And for a complicated system, synchronization of the actuators becomes painful. Next, please. So as an example, I have seen this Shung Powerball. Actually, it's not an advertisement, but the controller that Shung recommends is Keba Control, which is based on a PLC system. But Fraunhofer provided lots of toolboxes within ROS for operating with that Powerball, which operates in 100 Hertz, compared to Keba Control, which operates 125 Hertz. But in our project, based on MATLAB code generation, we developed, okay. Sorry, the last slide was more important, I think. Back, please. Okay. A controller with bandwidth up to 250 Hertz. But if you can see all three together, which is not possible now, but in ICRA conference, we can see that the controller provided by Fraunhofer was quite shaky. It's not a big difference between frequencies, but usually the accuracy of timer is not that much good. So just not about the speeds, it's about accuracy of keeping the time. About the way that we implemented, we published the article.
Thank you.
Thank you.
Look at that one.
Hi, my name is Cameron Finucane. I'm from Cornell University, and today I'd like to quickly introduce to you all LittleMop, which is a toolkit for high-level robot control that works with ROS. So as I'm sure you're all well aware, ROS has many powerful sensing and actuation capabilities, but the question remains on how to combine these or use these in a way to perform interesting high-level tasks. So say you have a robot and you want to have it be a waiter in a restaurant. And it'll receive customer orders from the two customers above and below the table and go to the kitchen and bring food to them when it's ready, when the food is ready. So commonly, one way to do this is just to write a bunch of code that glues together the low-level components. But the problem with this is that it's time-consuming, tedious, and you don't have really a guarantee that what you wrote is actually what you intended to have the robot do. So the alternative approach that I'd like to present here that LittleMop uses is instead to write your task as a specification in structured English telling the robot what to do and what not to do. And then from this specification, LittleMop synthesizes a controller automatically from the specification that is guaranteed to satisfy the task. So you can then use this controller to drive a robot. Here we see a simulated PR2 in Gazebo using ROS performing this task. It's using OMPL for motion planning and just the standard PR2 libraries for object detection and grasping. It's not the best waiter, but it did what we asked it to do. So another really powerful benefit of this approach is that if there's any possibility that the task you asked the robot to do might be impossible for the robot to do, LittleMop will fail to synthesize a controller and it will tell you about this problem at compile time. So this is an earlier version of the specification you saw before that's missing a key assumption. And what you can do then is LittleMop has a tool that lets you analyze the problem with a specification like this. So what you see here is this is a two-player game that you are playing as the robot trying to satisfy the specification against an adversarial environment. So we've received an order from a customer and we're trying to go to the kitchen to get the food to fulfill this order. But what we see here, when we go to the kitchen and try to pick it up, the tool tells us there's a conflict with the action that we just tried to do with a part of our specification where we said don't pick up food until it's ready. So by playing a game like this, we can gain insight into the problem of unrealizability of our specification, then go back, modify our specification, and resynthesize it to form a controller that will work. And because this task specification is high level, just by swapping out the low level controllers, you can have the exact same task run on pretty much any robot. This is a now doing the same thing in our lab. It's also sort of a mediocre waiter, but it's pretty cool. Please check out our website. We'd love to have you try it out, give us feedback. And I also want to mention this is joint work with Gangyun Jing, Vasamathi Raman, Hadaskis Gazit, and Catherine Wong. Thank you.
Hi, good afternoon. My name is Victor Mayoral Vilches. I'm the project manager at Earle. So just a quick survey. Who here wouldn't like to have its robot on its pocket? Well, I would love to. And that's exactly what we are doing at Earle project. We are trying to make a micro-aerial robot, a quadcopter, a small size. Here you have basically the size of our current prototype, which is being fabricated right now. All right? We are trying to integrate different technologies and standards, such as, for example, Wi-Fi, Bluetooth, USB, and stuff such as ROS and Linux. Right now, we are 8 students from different backgrounds and levels working on it. We have mechanical engineers, aerospatial engineers, we have electrical engineers, computer scientists, and so on, even guys and girls from marketing and business, etc. We are really passionate about this, and we are definitely open to any kind of collaborations, investment, whatever. So please, guys, if any of you just feel like collaborating, come to me, and I will be looking forward to whatever. Thanks.
You can play. Hello, I'm Gabriel Ribeiro, from the group of Robotics, Automation, Control and Automation of Federal University of Rio de Janeiro. And the new platforms of the oil company in Brazil, Petrobras, will be so far off the coast that we can't get to there with a helicopter and get back to the coast. So one of the alternatives is put some robots to operate this platform. Unfortunately, we can't put the robots on platforms just to test it, so we propose a simulation with a realistic visualization of industrial-like ambience on the platform. It's been developed with my group and associated group that's on Rio de Janeiro. It's based on Unity game engine, running now on Windows, and have several auxiliary visualizations to the robots. The robots and the sensors uses ROS messages, so it's standard and it's straightforward to use it with all the packages that are now for the community. And we aim to use these same messages to control the real robots. Then we can use the robots on real environments and virtual environments at the same time, and use things like a 3D visualization of the image with immersion of the operator, and the robots doing the same movement we can make he control some valves or objects on the virtual environment. And this is a top-sized simulation, and now we start to do some underwater simulation with ROVs, and it will be a fork of this. And this is a simulation of the old dual-arm motorman, and the next part will show a real motorman doing the same movements with the same message, so it can be done at the same time. Okay, thank you.
Can I use it by myself? No. Oh, this. Today, I'd like to advertise App Chooser and App Manager. App Chooser is an Android application, and App Manager is a ROS package. And they are useful for manipulating some kinds of robots and applications in a unified manner. And briefly, the function of App Manager is to supervise applications on each robot. And the function of App Chooser is interact with App Manager. And you can install the App Chooser from Google Play. Next, I'll tell you how to use them. Launch App Chooser, push add a robot, then you can see the pop-up window. To connect, you have to get RosMaster URI, and there are 3 methods. And ZeroConf fetches a new function of updated App Chooser. You can get all the robots on the local area network. Then you can see the robot list, so select one. And the next, you can see and get an application list. App Manager provides mainly 3 services. List apps informs available application. And please select one. Then you can run the .launch file in selected package. And you can also include the information of necessary client Android application, and then it is also launched. And finally, I'll show you the simple demo by using App Chooser. In this task, PR2 pick up the coffee can from fridge. And now Turtlebot is side of PR2. And put on the Turtlebot. And the Turtlebot automatically sends the coffee can to the master. I can drink it, thank you.
Yeah, hi, my name is Stefan Kohlbrecher from TU Darmstadt. I'm currently the team leader of Team Hector Darmstadt. We are involved in RoboCup Rescue, and you might have used some of our packages, which are all prefixed with Hector, whatever. Yeah, I wanted to give a short overview of what we do in RoboCup Rescue and what the RoboCup Rescue community is doing. So what is RoboCup Rescue? It's a competition, and there robots have to explore simulated disaster environments. In that regard, it's a little bit similar to the DARPA Robotics Challenge, minus the more crazy parts, like using humanoid robots for that stuff and so on. So yeah, and I know because I'm involved in both of these competitions. So yeah. So what we have to do is learn maps of environments. We don't have a map prior to getting our robots in there, we have to find simulated victims and manipulate the environment, or also observe using robot arms, for example. And you can use both autonomous and teleoperated robots. And as you can see in these pictures, the environments are pretty challenging because you have a lot of obstacles and your robots will fall over. It's not flat ground like you have in mobile manipulation oftentimes. So the next slide. So the issues we face in RoboCup Rescue is a reinvention of the wheel. So there was no code sharing. Everyone tried to develop their own SLAM stuff, for example, and a wide range of challenges. So there's a lot of teams with a mechanical engineering background that just don't do a lot of software stuff. So the idea is that the software teams help out the mechanical engineering teams and vice versa. So there's an initiative by the RoboCup Rescue community to provide basic building blocks for user robots based on ROS, and there have been events in the past, in the last 2 years, and there's also an upcoming event in Sweden. And yeah, we have a small video of how everything looks like. This is from the RoboCup German Open. This is from the RoboCup German Open competition, and this is our robot exploring the environment fully autonomously. The operator just told it that it has mapped the victim correctly, and now the robot is going on with exploration of the environment. These laser beams you are seeing are distance queries into the octomap we are using, because we are also mapping all these QR codes located in the environment. And yeah, a lot of that stuff here is available as open source also to other teams, or to you, of course, too. Yeah. And it's also, of course, also challenging because we decided to have an Ackermann-steered robot. So yeah, turning around is a non-trivial task there, but using a combination of different planning libraries, that works pretty well. So, oh yeah, and the full 20 minutes of our final mission are available on YouTube. So if you want to see more of that, you can do that. Okay.
Hi, my name is Hai Nguyen. I'm from Georgia Tech, the Healthcare Robotics Lab. My talk is titled Just Do It with ROS Commander. It's collaboration with Matei and Kajen at Willow, and it's a little bit of a jab on the Move It guys. So the problem that I'm interested in is getting general purpose robots to do multiple tasks. So we have all sorts of methods that work well for a single task on a single purpose device, and a single task on general purpose robots. So if you want to say like do door opening or pick up an object from a table, we have lots of good analysis methods for that. So to address this challenge, I introduced this interface called ROS Commander. So if you imagine Photoshop as a good interface on top of a lot of computer vision algorithms, this is an interface on top of a lot of manipulation-related algorithms. So the important thing about this is it uses the robot in the loop. So you can see here it's kind of, it's representing the behaviors that the robot that we construct with a finite state machine. But the important thing is that we have a robot in the loop so that when we finish constructing this state machine, we know that it works in the real world. And the thing that makes this work is that the state machine is kind of from previous work in mobile manipulation and work in graphics, and it seems like a state machine is kind of at the right level of complexity. So this is just a set of tasks that we've been able to do on our PR2 with these with the ROS Commander. So on top you see the PR2 opening a fridge with both arms and its base, and from just a basic set of parameterizable modules, we've been able to put together a lot of complex behaviors. So here the PR2 is handing over an object to a person. It's using tactile sensors in its hands, as well as parameterizing the trajectory with respect to the face detected. There's light switch, operating a light switch and operating a drawer. So what we found out with this is that a lot of tasks in home, because of the way home mechanisms is structured, they don't have a lot of pose variation. So once you have the pose of the robot, basically most of your house you can automate. So this is another example of what happens if you bring a robot into a home and you make it available to everyone. So in conclusion, I think that we focus on developing methods for operating multiple tasks on general purpose robots, we can go really far. And the important thing for such things is to test our behaviors on real robots, and that household mechanisms are low-hanging fruits because of small to no post variations, and that, good time. Thank you.
Hi, I'm Dave Coleman from the University of Colorado Boulder, and I would like to announce an open source robot platform for manipulation. It's the CLAM arm, and CLAM stands for Cheap Little Arm Manipulator because it's under $2,000, and it's got its problems because for that cheap of hardware, your tolerances and your accuracy of pick and place kind of commands could use some improvement. So I present this to you guys as a version 1, and anyone who's interested in this kind of thing, I encourage you to make a version 2. This could be some inspiration from the Turtlebot arms, you guys recall, but they're actually developed at the same time, roughly. So next slide. This one, it uses dynamical servos like many arms do. It's got 3D printed parts, Delrin. All the instructions to build are online. You can buy the parts on Shapeway. Road Narrow's website sells a kit that has it all. And so I just want to open a discussion that, open source hardware. Next slide. And then also, to me, more importantly, is the software side. It has the whole Move It software stack, and it's actually been running it since November. It used to be ArmNav, and I've ported it, and I want to encourage all of you guys to port your arm navigation software to Move It as well, so that more people are collaborating and working together on improving bugs and such in Move It and moving on with it. In this picture, we have it working in simulation, grasping, pick and place. This also has the perception, so it can detect it. It's kind of fully autonomous for that. And finally, there's a video to prove that it kind of works. This was back in January, so there's been improvements since, but I don't have a video. But again, this is good for do-it-yourself, hackers, teaching. We use this in our curriculum, teaching advanced robotics. So I throw that out there to you guys, and whatever happens to it. Thank you.
Hello, I'm Narcís Palomeras. I'm from the Underwater Robotics Research Center from the University of Girona, Catalonia. And I'm here to present a little bit about the underwater robotics, because underwater community also exists. It's not the most popular one, but we also exist. We have been developing underwater vehicles for the last 15 years. Some of them have been done for research projects. Some others have been done for teams of students in my university, in Girona. And we basically to participate to the Students Autonomous Underwater Challenge Europe. This is a students' competition that you have to bring your own underwater vehicle. We won the first edition in 2006, and we also won in 2010. This is not a students-made vehicle. This is a vehicle that we have been developing the last 2 years. It's for research projects. It contains a nice sensor suite. And it can go up to 500 meters depth. This vehicle is totally ROSified. What we do with this kind of vehicles, with underwater vehicles, basically we ask to the vehicle to submerge, to go until the depth of the sea, and when it is close to the sea bottom, it starts a lawn mover in a predefined area, and in this area, doing this lawn mover, it takes images and also records acoustic sensors. Then, when it comes back to the surface, if it comes back, we take all this data and try to do bathymetric maps, 2D mosaicings, 3D mosaicings. Also, we have did a very nice experiment lately that is attach an arm to our vehicle. It was nice because our vehicle was running its own architecture, the arm was running the other architecture, and they just share a ROS master, and everything was nice. We recovered a black box in a pool. It's in good conditions, but we were able to do this autonomously. And finally, just if you want to see our architecture, it's totally open source. It's in Big Bucket. And you can download also UWSim, that is, if you don't know, it's an underwater simulator, also based on ROS, and test a little bit with our vehicle. Also, if you know a little bit about the robot Pose IKF, we have developed another kind of robot Pose IKF. It's called Pose IKF Slam. It's similar, but with 6 degrees of freedom. It also, you can introduce emu, twist, and pose a standard message, and the output is an odometry. And if you are able to identify a landmark and give the relative position with your landmark, you have the SLAM for free. Thank you.
Hi everyone, my name is Gavin. In my spare time I run the Robots and Dinosaurs, the Sydney Hackerspace. So I'm coming from a bit of a different point of view than most people here. This isn't an actual educational institution, it's just a hobbyist club, it's people having fun on the weekends. You can see some of our workshop there. We share the workshop with people who actually make R2-D2s and Daleks. We've got a wide variety of people, wide variety of interests, 3D printing, laser cutting, sewing, all sorts of interesting bits and pieces. So I was hacking on the Turtlebot in the space, and a lot of people were asking me, you know, what is it, how can we get started, and all the rest of it, and there was enough interest that we decided to run a workshop. I just thought I'd share what went on, and I'd highly encourage people to do it even in an informal situation, because there's a lot of interest. So the background is our members, there's really no commonality between them. We have people that have actually submitted a lot of stuff to the Linux kernel. We have people that have never touched a command line. Basically, we had to make something that was sort of one size fits all, fits into a day, do whatever we could. So basically, have a bit of a mixture of theory, bit of mixture of practice. Every time we did an exercise, we followed up with what I call shameless bribery. So it's when we explain the concept of topics, it's publish some data on the topic. Okay, it's out there. First person to find it on the network gets a chocolate. The technique worked really, really well. I'd highly recommend it. So basically, it was just sort of cover as much as we can really, really quickly. We had a couple of Turtlebots running around, and my own one, which I call the Turquoise bot. Next slide. What I recommend if anyone tries to do, if anyone wants to do a workshop like this, is have a very standard machine configuration, because we had a lot of stuff running around at the last minute and making sure host IPs were set and all the rest of it. NTP, test your comms before it all starts. The robot inevitably gets flat, so I just had big extension cords plugged into it for most of the day. And because we had such a diverse background, I made sure to get Linux cheat sheets, the ROS cheat sheet, so everyone at least had a sort of common point of where to start. I think that's pretty much it. Following up. Obviously running the workshop is one step, but actually maintaining the community is another. So we started a Sydney local user group for ROS. We're having regular meetings in the hackerspace, and we're really encouraging people to bring along whatever robots they have and start tinkering away on it, show people what they've done. We have 2 members that are still in high school. They're both 15 years old. They've both made their own robots. They're actually irritatingly good robots. They're a lot better than some of the ones that we were working on ourselves, so that's encouraging to see. And the sort of tinkering nature and everything fits extremely well into a hackerspace environment, so I'd encourage people, if you haven't seen them already, to find your local hackerspace and say hi. So.
Hello, ROS users and developers. My name is John Bourne, some of you know me. This is just a last-minute lightning talk because I was talking to someone at lunch today and realized that I'd come across this website at one point. Actually, Ryan, do you think you could pull that up? There's this website called Bounty Source, and it's sort of like... I didn't see the joke, so... But anyway, so it's sort of, it has 2 sort of modes of interaction. One of them is a Kickstarter-like mode for open source software. The other one is direct integration with any bug tracker. And then you can just like pull out your wallet and take $5 out and put it down on a ticket. And the first person who comes and satisfactorily closes that ticket gets that $5, or the $5 or $10 or some odd dollars that anyone else puts down on it. So I thought as an open source community, this could be beneficial to us, and instead of sending an email out on the list, I figured I could speak it through loudspeakers. So check it out, see what you think. I created a ticket for a Smash ticket that I haven't put any money down on yet, but now that I've announced this, maybe I'll go put some money on there, and yeah, I don't know, maybe it'll work.
Pause that. Thanks. My name's Ian Sherman. I'm with Bot and Dolly in San Francisco. We're a small company that is trying to build bridges between automation technologies, including industrial robots, and the creative industry, including film, entertainment, stage, and that list is growing, architecture as well. So I'd like to share a little bit of what we're doing and then a couple thoughts of sort of lessons learned that might relate to some themes that have come up this weekend. So here's an example of some of the projects we work on. We got our start in motion control of film cameras. The word dolly in our name comes from film dolly, which is the wheeled cart that is traditionally used to move a camera around the set. We learned that the same platform we built for that project was applicable to a lot of other areas, some of which you've seen here. So I guess a couple things I want to mention. One, we were early adopters of the ROS Bridge and robot web tools, and we're big fans. Something that surprised me that was really nice was that ROS kind of provides this service-oriented architecture on the back end for you for free, and so we're able to leverage some client-side tools, things like Backbone, JS, and Knockout that can do rendering all on the client side. So it was really nice not to have to serve any HTML from the server. Those might be things that you all want to explore. Another thing is, I'm not ready for this one yet. Another thing is that this job that I didn't really know existed before I started working at Bot and Dolly was that of a rigger in an animation pipeline. So this is the person that builds tools for animators to work with characters. And there's some concepts there that have proven really useful to us in sort of building expressive tools for motion control. So rigger is used to allowing an animator to, say, blend between FK control and IK control when a character is reaching out, and then manipulating a doorknob. Okay, 3. I'd love to show you that video after the talk if you're interested.
Yeah, hi guys, I'm Dhananjay Sathe working on the RoboBot project at ETH, and this is something we've been working on of late, which I would like to share with you. Is it the right one?
Yeah.
Ways. They vacuum our floors, help us do great research, are fun to play with, and who knows, may soon bring us breakfast in bed. Doing these things well requires lots of computation, and the smarter we want our robots to be, the more computation and memory they need. This means our robots are often heavy and expensive. That's a problem. There's a better way. This new way means moving some of that computation away from our robots into the cloud, and that makes building smart robots much easier. Meet Robbie the robot. Each morning, Robbie prepares breakfast. but he is frequently intimidated by all the different breakfast foods. He has trouble recognizing the many different items and finds it difficult to pick them up with his gripper. In addition, he has trouble placing the items on the table because each morning the chairs are in different positions blocking his path. This means Robbie takes 5 hours to set the breakfast table. Frustration rises. Something has to give. One morning, Robbie decides to try something new, the Robo-Earth Cloud Engine. Now Robbie can move some of his heavy computation into the cloud. With the Robo-Earth Cloud Engine, Robbie can now take images of the different breakfast foods and ask the cloud to extract text and barcodes. If he has not interacted with a particular item before, he can run a graph simulator to figure out how he should pick it up. With the Robo-Earth Cloud Engine, Robbie can now take on many other tasks throughout the house instead of only making breakfast. Robbie is relieved, and so are his housemates. Robbie's friend Rosie is only equipped with an infrared sensor and a wireless module. She just transmits her sensor data, and the cloud takes care of all the localization and mapping. Using the Robo-Earth Cloud Engine, Rosie and Robbie can now collaboratively build and share the map of the house. Now both of them have less trouble moving around the chairs. With this accurate map and the Robo-Earth Cloud Engine telling her where she is, Rosie can now quickly collect all the crumbs under the breakfast table. The next morning, Robbie finishes setting the table in 50 minutes, and Rosie finishes to vacuum the entire house. And with his worries about buying expensive computers and constant system administration gone, their owner Igor can focus on what he really loves to do, building new robots. The cloud at your service, and all in open source, the Robo-Earth Cloud Engine.
Thank you.